Dear students, welcome to 25th online class of Control System Engineering. We are studying a chapter of System Design with the help of root locus. In last class, we studied about Introduction to Controllers, Ideal, Proportional Integral Control, and Lag Controller. The PI or lag controller is used to improve the steady-state error. With PI controller, we improve the type of the system and achieve a zero steady-state error, where in case of lag controller, we improve the steady-state error by a factor. Dear students, after this lecture, you will be able to design a controller to improve the transient response or transient specification of a system. Students, contents of this lecture are ideal proportional derivative compensator or PD controller and lead compensator. Dear students, now after improving the steady state error of a system, now we will improve the transient response of a system. The first technique we will discuss is ideal derivative compensation. With ideal derivative compensation, a pure differentiator is added to the forward path of control system. We will see that the result of adding a differentiator is the addition of a zero to the forward path transfer function. As this technique uses active network, we call an ideal derivative compensator a proportional derivative controller. Differentiation is a noisy process. Although the level of noise is low, the frequency of noise is high as compared to the signal. So differentiating high frequency noise gives us a large unwanted signal. The second technique, which don't uses pure differentiation, instead it approximates the differential process with the help of a passive network by adding a zero and a more distance pole to the forward path transfer function. The second technique uses a passive network is known as a lead compensator. Dear students, now we will study ideal PD compensator. The transient response of a system can be selected by choosing appropriate closed loop pole location on the S-plane. If this desired point is a part of root locus, then with simple gain adjustment, we can achieve the required transient response specification. Now, if the desired closed loop pole location is not on the root locus, then the root locus must be reshaped so that the root locus of the compensated system must pass through the desired location of closed loop pole. And with this, the desired transient specification will be achieved. Now, in order to reshape the root locus, poles and zeros can be added in the forward path transfer function to produce a new open loop function whose root locus goes through the design point on the S-plane. One way to speed up original system that generally works is to add a single zero to the forward path transfer function. Students, a zero can be represented by a compensator whose transfer function is of the form S plus Z. This function, the sum of differentiator and a pure gain, is called ideal derivative or PD controller. The ideal derivative compensation speed up the response of the system. For this demonstration, consider an uncompensated system whose root locus is given in the figure. The uncompensated system is operating at a damping ratio of 0.4. And now for compensation, we will add 0 of PD control at -2, -3 and -4. Dear students, in each design of adding the 0 at various locations in the system, for each case root locus is shown. The figure represents compensated system with a 0 at -2. System already have a pole at -2 and this causes a pole 0 cancellation. After adding a 0, the dominant pair of pole changes its location far away from the uncompensated one at a line of constant damping ratio. And each of the compensated system has dominant pole with the same damping ratio as of uncompensated one. So we predict that percent overshoot will be same for each case. Students, figure C and figure D represent root locus of compensated system for 0 added at -3 and -4 respectively. You will observe the change in location of dominant pair of pole as 0 moves towards the left, and with this gain is also decreasing. As in each case, dominant pair of pole is lying on line of constant damping ratio, so percent overshoot will be same. Students, in this table, the steady state and transience characteristic of uncompensated and PD compensated system for a 0 at location of -2, -3 and -4 are summarized. You will observe that in all the cases we have same percent overshoot, where other transients features like settling time and peak time are increasing as the 0 moves from -2 to -3 and then to -4. In second case, we have a 0 at -2 which cancel out a pole at -2, so this gave us a better second order approximation. Dear students, for the system given in figure 1, we have to design ideal derivative compensator such that the response of the system have 16% overshoot with 3-fold reduction in the settling time. If you analyze the forward part transfer function, it have 3 poles, one at origin, second at -4 and last pole at -6. First we will evaluate the performance of uncompensated system at 16% overshoot. For this, first we will draw the root locus of a system and we will draw a line of constant damping ratio. For this line of constant damping ratio, zeta equals 0.504 and angle will be equal to 120.26 degrees. Now we will find out the point where root locus intersects the line of constant damping ratio, and that will be our desired operating point. And this point is equal to minus 1.205 plus minus j 2.064, and for this point gain will be equal to 43.35. Dear students, now we will find settling time for uncompensated system operating at 16% overshoot. The settling time is equal to 4 divided by sigma, or 4 divided by zeta omega n, and this is equal to 3.320 seconds. Our evaluation of percent overshoot and settling time is based upon second order approximation, so we must check the assumption by finding third pole and justify the second order approximation. Now searching beyond 6 on real axis for gain equals that of dominant pair of pole, which is 43.35, the third pole is found to be at minus 7.59, which is over 6 times far away from the j omega axis as the dominant second order pair. So our second order approximation is valid. Students, now we will design compensator for the system. For this compensator, first of all we will find location of compensated system dominant second order poles location. For a threefold reduction in settling time, the compensated system settling time will be equal to 1.107 second, which is 1/3 of the 3.320. Now for settling time of 1.107 seconds, we will find location of dominant pair of pole. Now using the relation of settling time, which is equal to 4 over sigma, on rearranging, sigma will be equal to 4 divided by settling time, which is equal to 3.613. Now the real part is equal to minus 3.613 for dominant pair of pole, and to maintain the 16% overshoot, these poles must be on the line of constant damping ratio. So we will have a right angle triangle, and the imaginary part for dominant pair of pole will be equal to 3.63 tangent of 180 degree minus 120.26 degree, and this will give us damped frequency of oscillation equal 6.193. Students, here you will observe that the obtained desired point, which will have 1/3 of settling time, is not the part of root locus. Now to include this point in the root locus, we will reshape by adding compensator to the system. Dear students, now we will design compensator for the system to make the design point as a part of root locus. If the test point minus 3.613 plus j 6.193 is a part of root locus, then it must fulfill the angles criteria, which says that the sum of angles to the design point of all the poles and zeros of the compensated system except for those of the compensator 0 itself, and the difference between result obtained and 180 degree will be the angular contribution required for the compensator 0. And with the help of this angular contribution, we will find the location of compensator 0. Now using the open loop pole and the test point minus 3.613 plus minus J6.193, which is also the desired dominant second order pole location, we obtain that sum of angles equal minus 275.6 degree, and hence the angular contribution required for compensator 0 for the test point to be on root locus will equal its difference with 180 degree, or we can say that 275.6 degree minus 180 degree equals 95.6 degrees. So we will add a compensator 0 to a system which will add angular contribution of 95.6 degree, and with this angles of poles and zeros of open loop system with the desired test point will be equal to odd multiple of 180 degrees, and this point will become the part of root locus. Students, now using the geometry given in the figure, we will find the value of sigma, which will be the location of compensator 0 with angular contribution of 95.6 degrees. Solving the trigonometry, we found that sigma equals 3.006, and the complete root locus for the compensated system is shown in the next slide. Dear students, figure 1 represents complete root locus for the compensated system, which have percent overshoot is equal to that of uncompensated one, but its settling time is 3 times reduced to that of uncompensated one. And this can also be observed in figure 2, which represent step response for both compensated and uncompensated system. You can observe clear difference in the speed of response. The compensated system quickly stabilize and enter the steady state, where uncompensated system takes much time. Dear students, the ideal derivative compensator used to improve the transient response is implemented with proportional plus derivative controller. The transfer function of the controller is GC of S. In this, sum of proportional error and derivative error are forwarded to the plant. Here K1 over K2 is chosen to equal the negative of compensator 0, where K2 is chosen to contribute the required loop gain. Dear students, now we will study lead compensator. Just as active ideal integral compensator can be approximated with a passive lag network, similarly an active ideal derivative compensator can also be approximated with a passive lead compensator. The advantage of passive lead network over the PD controller are no additional power sources are required, and noise due to pure differentiation is reduced. Where the disadvantage is that additional pole doesn't reduce the number of branches of the root locus that crosses the imaginary axis and enters into right half plane, where the addition of single zero of PD controller reduces the number of branches of the root locus that crosses G omega axis and enters into right half plane. Dear students, now for lead compensator, if we select the desired dominant second order pole on the S plane, then the sum of angles from the uncompensated system poles and zeros to the design point can be found, and the difference between 180 degrees and the sum of angles must be the angular contribution required of the compensator. Now look at the system given in the figure. The uncompensated system have 2 poles and 1 zeros. Poles are represented by P1 and P2, where 0 is represented by Z1, and desired location for dominant second order pole is also given, and respective angles for each vector are also mentioned. Now to this system for compensation, we add a lead compensator, which have a compensator 0 and compensator pole, and their vectors are also connected to the desired point, and respective angles are also given. Now if our desired point is a part of root locus, then it must fulfill angles criteria, which says that sum of angles of zeros minus sum of angles of poles must be equal to odd multiples of 180 degree. Here theta 1 represents angular contribution of compensator pole, where theta 2 represents angular contribution of compensator 0. So their difference theta 2 minus theta 1 will be equal to the angular contribution of lead compensator. From the figure, you can observe that theta c is the angle of ray extending from desired point and intersecting the real axis at compensator pole and compensator 0. Or we can say that theta c is the required angular contribution for lead compensator to make the desired point a part of root locus. Students, now this can be visualized that the ray rotating about a desired closed loop pole location and intersecting the real axis at compensator pole and compensator 0 as shown in the figure. We realize that an infinite number of lead compensator could be used to meet the desired transient response requirement. And for this, we arbitrarily select either a lead compensator pole or 0 and find out the angular contribution at the design point of this pole or 0 along with system's open loop poles and zeros. The difference between this angle and 180 degree is the required contribution of the remaining compensator pole or 0. Dear students, in the given problem, we have to design 3 lead compensators for a system that will reduce the settling time by a factor of 2 while maintaining 30% overshoot, and we will compare the system characteristics between the 3 designs. Students, in the solution, first of all, we will sketch the root locus of the system, And for overshoot of 30%, we will find value of damping ratio zeta, which equals to 0.358, and for this we will draw line of constant damping ratio zeta, which will have an angle of 110.98 degrees. Now along the line of constant damping ratio, we will find out the point where root locus will intersect this line. And the uncompensated system intersects the radial line at point -1.007 plus j 2.627 with gain of 63.21. And for this we will have a settling time of 4 divided by sigma, which equals 3.972 seconds. Dear students, now we know that settling time of uncompensated system operating at 30% overshoot is about 3.972 seconds. Now we will find required settling time and location of dominant pair of poles. We required two-fold reduction in settling time, so our new settling time will be equal to about 1.986 seconds. Now we will find design point for this settling time. Using the relation of settling time, the real part of design part will be equal to minus sigma, which in turns be equal to 4 divided by settling time, or minus 2.014. Now the compensated system will also have the overshoot of 30%, which means that new dominant pole will also lie on the radial line. Now considering a right angle triangle and using trigonometry, the imaginary part will be equal to 5.252. Students, now in the problem we have to design 3 lead controller. For first lead compensator, we will choose the location of -5 for compensator 0 on the real axis. Now we will find sum of angles of uncompensated system poles and the 0 added at -5 to the new design point, and will find its difference with 180 degree. The sum of angles here equal 172.69. The difference between this angle and 180 degree is the angular contribution required from the compensator pole in order to make the new design point as a part of root locus. So angular contribution of minus 7.31 degree is the required from the compensator pole. Dear students, after finding the required angular compensation required from the compensator pole, we will use the geometry to find out compensator's pole location. Now using figure and applying trigonometry, we get the result that compensator pole will have a location of -42.69. Now in order to justify our estimates of percent overshoot and settling time, we must show that our second order approximation is valid. Students, now to perform this validity check, we will search for third and fourth pole of the closed loop system. Third pole is found beyond -42.96 and the fourth pole will be between -5 and -6 as shown in the figure. Now for this region, and again equal to that of compensated dominant pole, which is 1423, we will find that a third pole and fourth pole are at minus 43.8 and minus 5.134 respectively. Since minus 43.8 is more than 20 times far away from the real part of dominant pole, so the effect of third closed loop pole is negligible, where the fourth closed loop pole is at minus 5.134 and it is close to the 0 at minus 5. So at this point we have pole 0 cancellation. So we conclude that our second order approximation is valid. And with this, our first lead compensator is completed for the given system. And second and third controller are designed with the same procedure by placing a compensator 0 at minus 4 and compensator 0 at minus 2. Rest of the steps are the same. Dear students, the dominant pair location, the transient specification, location of 0, and location of other poles are summarized in this table. For uncompensated system, for lead compensator with 0 at minus 5, for second lead compensator system with 0 at minus 4, and for third compensated system with 0 at minus 2. Dear students, this figure represents step responses for uncompensated system and 3 lead compensated system. You will observe a clear difference in the response of compensated system with uncompensated one. Now if any of you have any questions, please ask.